Tribhuvan Prasad Yadav, and I've done my graduation from BHU and my masters from IIT Hyderabad. So guys, we are going to study chemical equilibrium today. First of all, let us understand what does equilibrium means. See, equilibrium simply means that whenever the rate of forward reaction becomes rate of backward reaction. Okay sir, how does it happens? See, simple, you have to see that if there is a reaction happening A to B, then the rate of formation of B and rate of formation of A, when both of these become equal, the time at which both of these rate become equal is called chemical equilibrium. Okay sir, is there anything called physical equilibrium too? Yes, equilibrium can be of two types, physical or chemical. You have to remember just for general knowledge purpose. Okay sir, physical equilibrium is what? Physical equilibrium is something that you can see in daily life. You can see, for example, evaporation of water. Water in liquid state converted into water in vapor state, gaseous state. So reactant and product both are same. Both are water, H2O. But their state is different. Their properties are different. Then it is called physical equilibrium. Okay sir, physical equilibrium is what? The temperature, it happens at 100 degrees Celsius, we all know. That temperature at 100 degrees Celsius, when water will be present in both liquid as well as in gaseous phase. And this is similar case with the ice also, solid, H2O solid, at 0 degrees Celsius. Okay, at that time, they both are in physical equilibrium. Got it? And another example can be sodium chloride. You all know sodium chloride, the table salt that you all eat. Okay, this sodium chloride, when it is in equilibrium with the aqueous, when we mix water, or normally how table salt is made, we pour out some salt water and evaporate the water, then it becomes a solid that we can eat. This is a simple process that we all do. So these all are example of what? Physical equilibrium. Why? Because the reactant and the product are same. Okay sir, then what is the example of chemical equilibrium? We can see also that. Let us see the examples of some examples of, sorry for the handwriting, I'm writing very fast right now, that's why. Let's see some example of chemical equilibrium. For example, hydrogen plus iodine gives what? HI. It's a very basic reaction, 2HI. You can see this symbol, it represents equilibrium. Okay, it means equilibrium has been attained. Okay sir, what does it mean? It means that the rate of formation of hydrogen iodide is equals to the rate of dissociation of hydrogen iodide. Dissociation means what? It is again dissociating into hydrogen iodine atoms. You have to think very carefully and understand the concept very carefully. Okay, I'm speaking again, telling again. The rate of formation of HI, it means what? Hydrogen and iodine are combining to form HI. And at the same time, HI is dissociating again into hydrogen and iodine. This is called chemical equilibrium. The time at which this is happening, when the rate of forward reaction is equals to rate of backward reaction, it is called equilibrium. So this is all about chemical equilibrium. Now we are going to dive deep into the concept. Okay, this is in gaseous phase. The phases are also important. Okay, there's something called this square boxes. This represents the active mass. You have to learn this concept also, because we are going to do some numericals in further lectures, and it will help us in that thing. Okay sir, what is active mass? It is nothing but it is just the concentration, I would say the mole per liter, the concentration. Okay, it is mole per liter concentration. Okay, of what? Of gaseous atom. You have to remember that only gaseous atom. In this, all of three are gaseous items, so we can take the active mass of all three. Active means what? Which is active, which is actively participating in a reaction. And what participates in a chemical reaction? Generally the gaseous parts. They collides very quickly to make the products. So this is all about active masses. Let's dive further. This was all about chemical equilibrium. Let's move to the law of mass action. Since this is a demo video, I'm going to a bit fast so that I can cover most of the topics. Law of mass action. Okay, sir, what will happen with this thing? We will find the K, that is the equilibrium constant. This is very, very important in all higher studies also. Now, what is the equilibrium? What does this equilibrium constant means? Okay, first of all, it does not depend on concentration. It only depends on temperature. Only depends on temperature and many other factors. But listen to me carefully. What happens when a temperature increases? Collision increases. Collision increases, the number of products formed will be increased. Okay. So K is what just giving us a basic idea how the reaction is happening. Is it happening very fast? It is happening very slow. Is it going in forward direction? Is it going in backward direction? So this is all the things. I mean, the rate and the direction is told by this K. Okay, so this is very important, and it does not depend on concentration. It depends only on the temperature. You have to just remember this concept and these things very carefully. And I hope you understand all these things. Let us move and derive this law of mass action. Suppose there is a reaction AABB is in equilibrium with CCDD. And what is small d and capital D means? Small a here is the stoichiometric coefficient. For example, here you would say this 2, which we used to balance the reactions. Now, this is called the stoichiometric coefficients. These are called the stoichiometric coefficients. Okay, these are called the stoichiometric coefficients. Similarly, B is also the stoichiometric coefficient of B, and C is for C, small d is for capital D. And what are capital A, capital B? They are the atoms or molecules who are participating in the reactions. A and B are the reactants, and C and D are the products. Okay, sir. Let's move further. Let us assume all of them are the gaseous phases. So we have to consider the all active masses. Okay. Okay, sir. So how do we write a chemical reaction? Let us see. This is a chemical at time t is equals to 0. And what does it mean? Time t is equals to 0. It means that the reaction has not yet been started, but it is going to start. Okay, it means we are just holding the test tubes and we're just going to mix them and see what happens next. Okay, so it is the initial time, small a, capital A, small b, capital B. Okay, sir. And what does this means? At time t is equals to equilibrium. It means the time at which rate of forward becomes rate of backward, what are the concentration of C and D and all. Okay. Let us stop for a moment and derive the equation for K. See, this is the rate of forward reaction when the C and D are forming, and this is the rate of backward reaction when A and B are forming from C and D, because reaction is going in reverse direction. I hope this is what you understand. Okay. Okay, sir. So RF is what? Directly proportional to the rate of forward reaction is rate of forward reaction is directly proportional to, let me reduce the eraser. Rate of forward reaction directly proportional to the concentration of what? Products. Okay. So the rate of forward reaction directly proportional to concentration of reactants, because how much rate is going forward, how much products are forming depends on the concentration of reactants. If you increase the concentration of reactants, obviously the product will increase. Got it? So rate of forward reaction depends on concentration of reactants. Similarly, rate of backward reaction depends on the concentration of these reaction. Now for this reaction, backward reaction, these are the reactants. Now for rate of backward reaction, these are the reactants. The concentration of C to concentration of D. one more most important thing, that you have to use the stoichiometric coefficients as the power of these active masses or the concentrations. For example, capital A, the stoichiometric coefficient is small a, so we have to put the power A. Similarly here, small b, similarly here C, small d. I hope you also understand. Let us move. So when we solve this, we will get Rf is equals to, when we remove this proportionality constant, we will get another constant Kf, that is the rate constant for the forward reaction. Are you getting the thing? And rest will be same, small a, capital B, small b. Okay. Similarly, we will get rate of backward reaction is equals to rate constant of backward reaction into the concentration of C into concentration of D. Okay, sir. And what this is equation 1, this is equation 2. And what I had said, at equilibrium what will happen? At equilibrium, rate of forward become rate of backward. Rate of forward becomes rate of backward reaction. It means what? These 1 and 2 are equal. It means what, sir? Kf is equals to Kf into A small a capital B small b is equals to Kb capital C small c capital D small d are equal. Okay, these two are equal. Beautiful. Beautiful. What does it mean, sir? It means Kf, when I bring this Kb here, Kf upon Kb is equals to concentration of C into the power C capital D to the power D, A to the power A, and B to the power B. What I did, I just brought this here. I just brought this here and these whole terms in the division there. Okay. So now what we will get? See, Kf upon Kb is another constant that is called Kc. Remember, equilibrium constant. This Kc is what? Nothing, Kf upon Kb. This Kc is what? Kf upon Kb. Remember this thing. It means what, sir? It means Kc will become small c to the power small capital C to the power C small c capital D small d capital A small a capital B small b. So this is the final equation that you will derive, that you will get. Okay, maybe the color is very bad. I think I should remove it, but you need to understand what I mean. It means Kc is equals to, this is the formula that we'll get for the equilibrium constant, and these are used in the most of the numericals that we'll see in this chapter. I hope you all understand this thing. Okay, sir. Can we see some examples? Yes, sir. We can see some examples. Let us see for the simple that we just had seen. Hydrogen plus iodine gives 2Hi. What will happen here? If I have to find this Kc for here, so Kc will be what, sir? Now you have to see that if basically is what? Kc is equals to reactant concentration of product. These are the product, na, C and D. These were the product for this reaction, if you remember. Similarly, A and B were the reactants. So what is Kc means is concentration of product divided by the concentration of reactants. Hope you understand. Similarly, here product is what? Hi. So we will use the active mass of Hi or concentration of Hi. Now you have to see the stoichiometric coefficient is 2. You have to use the power 2. Very good. Very, very good. Similarly, the reactants are S2 and iodine in the multiplication. So you can see how I derived the equation equilibrium constant for this reaction. Okay, sir. Let us see some more example. For example, PCl5 in gaseous phase gives PCl3 plus Cl2 gas. Can you see this? Okay, sir. This is a reaction. Can we find the Kc for this reaction also? Yes, sir. Now the products are PCl3 and Cl2. PCl3 and Cl2. And the reactant is what? PCl5. And it is already a balanced reaction. There is no extra stoichiometric coefficient. So we don't have to put anything in power. This is a very basic reaction. Okay. So there is a homework you can do by yourself. Half hydrogen plus half iodine gives Hi. Just stoichiometric is different. Now find the equilibrium constant for this reaction. This is your homework. And thank you for this session only, and hope you understand this concept. You can and thank you. Bye.